Hi, this is a presentation of the different numbering systems that we are using in networking. And we start off by looking at our normal numbers, which is also called decimal numbers. Here we have a base in the number 10. That means that we have 10 different digits from 0 up to 9. And all the numbers that we know are a representation by these 10 different digits. This is a position-based numbering systems, and we know that because here we have the number 9872, and we know these are the ones, these are the tens, these are the hundreds, and these are the thousands. And this is because actually what we are doing is that we are looking at the different positions that the digits are placed in. This is the ones, which means 10 in the power of 0. So this is actually the zeros position. Here we have 10 in the power of 1, which is the first position, second and third. So we just multiply it with the 10 in the power of the position. And this is actually how we get the number 9872. The reason why I'm telling you this is because it's actually the same thing that we are doing in binary numbers. Here the base is 2, which means that we only have 2 available digits. And every number is consisting of only two digits. This is also a position-based numbering system, but we can see here the position is denoted by 2 in the power of the position. So because 2 is the base number, here everything is in the position is in the power of the 2. So here, for instance, we have a binary number called 101101. And to calculate that into normal decimal numbers, we just do what we do without thinking about it in the decimal numbering system. We take that this is 1 multiplied with 2 in the power of 5, 0 multiplied with 2 in the power of 4, 1 multiplied with 2 in the power of 3, 1 multiplied with 2 in the power of 2, 0 multiplied with 2 in the power of 1, and 1 multiplied with 2 in the power of 0. And what we do here is that we add them all up, and when we do that, we know that 1 multiplied with 2 in the power of 5. 2 in the power of 5 is 2 multiplied with itself 5 times, and that is 32, plus 0, plus 1 multiplied with 2 in the power of 3, which is 8, plus 1 multiplied with 2 in the power of 2, which is 4, plus 0, plus 1 multiplied with 2 in the power of 0, which is 1. And when we add them all up together, we will see that this gives us number 45. So let's try to do that with some other numbers. So I'll just turn on my, that's it. So if we were going to calculate the number 10, it's actually called not 1010, it's called 1010. This is a binary number. What is the decimal number here? So again here we say we look at the position. So this is the 0th position, 1, 2, 3. So this gives us 1 multiplied with 2 in the power of 3 plus 0 multiplied with 2 in the power of 2 plus 1 multiplied with 2 in the power of 1 plus 0 multiplied with 2 in the power of 0. We know that 2 in the power of 0 is 1. 2 in the power of 1 is 2. 2 in the power of 2 is 4. 2 in the power of 3 is 8. 2 in the power of 4 is 16. 2 in the power of 5 is 32. 2 in the power of 6 is 64, and 2 in the power of 7 is 127. So here we have 1 multiplied with 2 in the power of 3, which is 8, and whatever we multiplied with 0 is 0. 1 multiplied with 2 in the power of 1 is 2, plus 0, which is 10. So 10 is the decimal value of this binary number. Just to make sure we know the difference, I put a small 2 underneath here, which indicates that this is a binary number and this is a decimal number. Okay, so let's try the other example here. It's 1, 1, 0, 0, 0, 1, 1. So this is the 0th position, the first, the second, the third, the fourth, the fifth, the sixth. Okay, so this is 1 multiplied by 2 in the power of 6 plus 1 multiplied with 2 in the power of 5 plus 0 multiplied with 2 in the power of 4 plus 0 multiplied with 2 in the power of 3 plus 0 multiplied with 2 in the power of 2 plus 1 multiplied with 2 in the power of 1 plus 1 multiplied with 2 in the power of 0. So 2 in the power of 6 is 64 plus 32, which is 2 in the power of 5 plus 0 plus 0 plus 0 plus, and this is power of 1, which is 2 plus 1. So this gives us altogether, if we add them up here, it will give me 99. So this number here in binary represents the same as 99 does in decimal number. So it's just another way of writing the same number. This is of course how everything is saved in computers, because computers have two levels, on and off, which is binary, more or less. So that was some examples about that. Of course, sometimes we also want to go from binary to, or from decimal to binary. And how can we do that? Well, we can use different types of methods to do that. I will show you the division method, which is something that will apply to all different types of numbering systems. So what we do is that we divide by the number, the base number of the numbering system that we would like to convert to. So in this case here, I would like to convert from decimal to binary. So what I do is that I take, in this case, 30 and divide it by 2, because I'm going to convert to binaries. This will give me a full time, or 15 as a result, and it's full time, it's a full number. So that will give me a remainder of 0. So then I take 15, divide by 2, which is 7.5, which means that it has a full time of 7 and it has a remainder of 1. Then we take 7 and divide by 2, which is 3.5, which gives me a full time 3 and a remainder of 1. Take 3 divided by 2, which gives me 1.5, which is a full time 1 and a remainder of 1. Then I take a half, or take 1 divided by 2. I continue to divide by 2 until I reach 0 here, and this gives me 0.5, which gives me a remainder of 1. As you may see, these remainders will now make up the binary number, and I do it from the bottom and up. So 30 in decimal numbers is 11110 in binary. So this is how we convert the other way around, by dividing by 0. So let's try to do that as well. So here, if I have the number 100, I would like to find the binary number for 100 in decimals. So what I do is I take 100 and divide by 2, which gives me 50. And that is a full number. So I have a remainder of 0. I take, 50, divide by 2, which gives me 25 and no remainder. Then I take 25 and divide by 2. Well, this gives me actually 12.5, so it's 12 and a remainder of 1. Then I take 12 divided by 2, which is 6 and a remainder of 0 because it's a full number. And then I take 6 and divide by 2, which gives me 3 and a remainder of 0. I take 3 divided by 2, which is 1.5, so it's 1 and a remainder of 1. And then I take 1 and divide by 2, which is 0.5, which is 0 full number and a remainder of 1. So here again from the bottom up, 100 is the same as 1100,100 in binary. So 100 in decimal numbers equals 1100,100 in binaries. Next example, 64. We want to convert that into binary. So divided by 2 is 32, and it's a full number, so I have a remainder of 0. 32 divided by 2 is 16. Again, remainder of 0, full time. 16 divided by 2 is 8 and remainder of 0. 8 divided by 2 is 4 and a remainder of 0. 4 divided by 2 is 2 and a remainder of 0. 2 divided by 2 is 1, and again a full number. And again a half, or 1 divided by 2 is 0, and here I get a remainder of 1. So 64 in decimal numbers equals 100,000. 1, 2, 3, 4, 5, 6. Yes, in binaries. So this is the way that we convert from decimal numbers to binary numbers. And that was it about the binary numbers. We also have one last numbering system to cover, and that is the hexadecimal numbers, which is also called base 16, because here we have 16 different digits. And we don't really have that, so we use letters as digits. So here we have the numbers from 0 to 9, and then we start by using letters A, B, C, D, E, and F, which gives us altogether 16 digits. We use hexadecimal numbers to represent large binary numbers. So the correlation between binary digits and hexadecimal digits is that 4 binary digits is 1 hexadecimal digit. And this is also a position-based numbering system. Here the base is 16, so everything is denoted in powers of the number 16. So, but we do the exact same thing. Here we have an example where we have 4A6, and we can see here that this is the 0th, the 1st, the 2nd position. So we say here that this is 4A6. If we want to convert that into decimal numbers, we take 4 multiplied by 6 in the power of 2, because it's in the 2nd position. A multiplied with 16 in the power of 1 plus 6 multiplied with 16 in the power of 0. So here, this is 4 multiplied with 256, which is 16 multiplied with 16, plus 10. A here is 10, because here we have 9, 10, 11, 12, 13, 14, 15. So this is 10 multiplied with 16 plus 6 multiplied with 1, which is, when we add them all together, 1190. So 4A6 is the same as 1190 in decimal numbers. I think I'll only do one example here because I think you get it now, and this is just annoying big numbers to work with. But let's try FF. It's a hexadecimal numbers. This is the 0th position, this is the 1st position. So when I want to find the decimal value, it's F multiplied with 16 in the power of 1 plus F multiplied with 16 in the power of 0. And this is F is 15 multiplied with 16 plus 16 multiplied with 1. 16 in the power of 0 is 1. And this is 240, and this is 15. F is 15, and this gives me 255. So here, FF in hexadecimal, small 16 on the bottom, indicates hexadecimal is the same as 255 in decimal numbers. Here, if I want to do the opposite now, if I want to go again from decimal numbers into hexadecimal, so I have 145 in hexadecimal. Sorry, this is not in hexadecimal, it's in, sorry, I just checked that. 145 is a decimal number. I want to find the hexadecimal number here. So what I do here is the same thing as I did in binary. I divide by the base of the number I want to convert into. So I want to convert into to hexadecimal, and the base is 16. So I go and say how many full times will 45 go up in 16. So I take 145 divided by 16, which will give me 9 point something. So it's a full 9 times, and then I have a remainder. And to calculate the remainder, I take 145, I take 16 multiplied with 9, which is here, the full time that it goes up. And when I calculate this is 144, it will give me a 1 in the remainder. Then I take 9 and divide, because here is the rest. 9 divided by 16 is 0, and the remainder here is 9 minus 16 multiplied with 0, which is 9. So 145 is then a hexadecimal, or 145 in decimal is 91 in hexadecimal numbers. It's really a little bit more annoying to calculate because the numbers are bigger, but the idea and the principle is the same thing, the way that we're doing. I will not show you an example now. I think we will do that later on in class. The good thing, though, is when you want to go from binary to hexadecimal, you can just divide the number into the columns of 4 and then convert it. Here, for instance, I have 1, 0, 1, 0, 1, 1, 1, 1. And I start from the back and I take the first 4 and look at see what is the hexadecimal value of 4 ones, and I go up here and I see, okay, that's F. So that is the last digit, is F. And then I take the next 4, which is 1, 0, 1, 0, and I go up here and I find 1, 0, 1, 0. Where is it? There. So it's A. So this is just AF. So we just need this one. You don't need anything more, and then just divide them into different categories or columns of 4. Then it's quite easy to go from binary to hex. And actually the opposite way also. You have A and you just convert that into this one, and you have F to convert it into here. So that is why we are using hexadecimal numbers, because it's so easy to, instead of having a huge number of digits in a binary number, we will shorten it and have few hexadecimal digits instead, representing the exact same number. And that was it. Thank you.